Welcome again to Waidsum Academy. Here is part 2 of indices. Today we're looking at the fourth law. In the first part of this video, we holistically treated part 1, and in part 1 we covered the first law, second law, and third law of indices. Today we're looking at the part 2, which covers the fourth law, the fifth law, the negative indices, and the exponential indices and the fractional indices. So we're going to try as much as we can to quickly run through all of this. So let's start with the fourth law, and let's expatiate on that. Let's take a look at some examples to illustrate the fourth law of indices. Okay, some example to illustrate the fourth law. Now, if we're looking at the fourth law, if, for example, before we expatiate on that, let's give something that symbolizes the fourth law. Something that symbolizes the fourth law. For example, if you have 4 times 3, if we have 4 multiplied by 3, 4 multiplied by 3, then everything put together in one bracket, both of them put together. You can see the numbers are put together in a bracket, but the power, it's outside talking to both of them. The power is outside talking to both of them. For example, I keep these 3 as the power outside. So what this means is that this will be talking to both of the numbers inside. So this will be exclusively equal to 4 to the power of 3 individually, 4 to the power of 3 and multiplied by 3 to the power of 3, multiplied by 3 to the power of 3. What we've done here is that this power, because of this bracket, it's talking to both these two numbers inside. And you cannot use first law because the bases are not the same. You see, this base is different from this base, so you cannot use first law. You only use first law when these bases are same. If this is 4, this is also 4, then we can use first law. So what do we have here? It's not we cannot use the first law. So we just wrap it up here. So this is what is going to lead us to what we call the fourth law. This is what is going to lead us to fourth law. Like you have s plus t raised to a certain power. Another example, s plus t raised to a certain power. Then we know that the power, whatever power this is, let's say raised to the power of 4, whatever power this is talking to both the two things inside the bracket. This power is talking to both of them inside the bracket. So what this simply entails, let's say this is a Roman figure 1 and this is our Roman figure 2. We're trying to illustrate with many examples before we generalize the law. What this entails is this gives you s to the power of 4. Each of them individually will be raised to the power of 4. Each of them individually will be raised to the power of 4. Okay, each of them individually. Okay, sorry, this one is multiplication. Okay, it's usually multiplication. Then this one will become t times t to the power of 4 multiplied by t to the power of 4. So the power outside is talking to both things that are inside the bracket. The power outside is talking to both of these things inside the bracket. So that leads us to a general law called the fourth law. Now, which means in a summary, if you want to write the fourth law, you can simply say a times b, a multiplied by b, okay, a multiplied by b to the power of any other letter. Let's say we say n to the power of n, a times b to the power of n. Then this will be simplified as a to the power of n and times b to the power of n. This will be simplified as a to the power of n. Why? Because this power is talking to this one inside the bracket and also this one inside the bracket. So multiply by, remember, you see these two numbers inside the bracket, they are being multiplied. Multiply by b to the power of n. Multiply by b to the power of n. This is what we call the fourth law. Is that okay? Now let's take a look at example and simplify some more case. If they have the same, it will not be fourth law. This will now be like first law. Because when you expand, if they have the same base, this and this have the same base, to be a to the power of n times a to the power of it will just be very easy to know if they have the same base. Now let's take a look at an example. Let's say you are given m to the power of, let's say, question 1. Let's solve this. M to the power of 3, m to the power of 4, multiply by n, then to the power, everything to the power of 3. Everything to the power of 3. So if everything is to the power of 3, you must put bracket to show that it's talking to the power here is talking to everything inside the bracket. So I'm going to put 3 here. Okay, the power of 3 here. Now what this means is that this 3 is talking to this and is also talking to this. So to evaluate, you write m. You can see m has its own power first. The power is what? 4. So this is third law. You know, this one times the power outside. So you will multiply. This one is a small third law that is being applied here. Multiply by 3. Then you say times n to the power of 3. Times n to the power of 3. Okay? This one, because n is 1. 1 times 3 is 3. Okay? N is power 1. 1 times 3 is 3. So that's why we have n to the power of 3 here. That's why we have n to the power of 3 here. So the next step is to evaluate this one. So 4 times 3 is 12. So I have m to the power of 12. M to the power of 12. And then I have n to the power of what? N to the power of 3. N to the power of 3. So this is your final stage. This is your final stage. Is that okay? This is your final stage. Is that okay? Quickly. Now let's move on quickly. Let's take another example before we go to fifth law. Let's take another example. Before we go to fifth law. Let's say we have number 2. Let's say we have 3xy to the power of 3. We have 3x. And then y to the power of 3. Then everything to the power of 2. Everything, bracket everything, close it in a bracket, everything to the power of 2. So what you have here is the power of 2 here is talking to every number and every alphabet inside this bracket. So what if you have to evaluate, it means this 3 will be raised to power 2, which will mean 3 times 3, which is 9. And then you say times, multiply by x. This x will be raised to power 2 because that power 2 is talking to everything in the bracket. This power 2 is addressing everything inside this bracket. Okay, so this x to the power of 2 and then multiply by y to the power of 3, y to the power of 3, then times this 2, because this one already has its own power, you multiply with the 2. That's third law. You remember third law. Anything that already has power and there's another power outside, you multiply. So what we have at the end of the day, here we have 9, not 6, okay? Many of you write 6, you will be wrong. 9. 3 times 3 is 9. So times, multiply by x squared. Okay, multiply by x squared. Then multiply by y to the power of 6, because 3 times 2, this power, 3 times 2 is what? Is 6. So it will be y to the power of 6. Y to the power of 6. Now let's write in final notation. We have 9x squared. We have 9x squared. Okay, 9x squared. Y to the power of 6. 9x squared. 9x to the power of 2. and y to the power of 6. That's our final case. Okay, so that's the second case. Now we do one more before we go to we take one more example before we go to before we go to the fifth law. We take one more example before we go to the fifth law. Now let's say example 3. Let's say example 3, we have 7p to the power of 4, 7p to the power of 4, r, then we have r, and then we have s to the power of 5, x to the power of 5, and then we close a bracket, and then we say everything to the power of 0, everything to the power of 0. Okay, so I can tell you, without solving this, I can tell you the answer is going to be 1. The answer is going to be 1. Why? Anything to the power of 0 is equal to 1. All this to the power of 0 is going to be 1. However, we have to do it one by one to show you how the answer is 1. So let's say we take it, everything in the bracket. So you say 7 to the power of 0, 7 to the power of 0, multiply by p to the power of 4 times 0. P already has 0 power. The power is 4. But you have to use it to multiply that. Use it third law. Not the fourth law now, use the third law. This power for p will be multiplied by 0. So you say p to the power of 4 times 0 times 0. Then the next one, you have r to the power of 0. You have r times r to the power of 0. Okay, this times r to the power of 0. Then times times s to the power of 5 times s to the power of 5 multiplied by 0 times s to the power of 5 multiplied by 0. Right? This is what it is. So now we look at them one after the other. We look at them one after the other. Now the next one is simply to say 7 to the power of 0 is 1. Any number to the power of 0 is 1. So I say 1 times p to the power 4 times 0. Okay, 4 times 0 is 0. P to the power of 0 will be 1. R to the power times r to the power of 0. R to the power of 0 is 1. R to the power of 0 is 1 times s to the power of 5 times 0 is 0. Then s to the power of 0 is 1. So 1 times 1 times 1, everything will be equal to 1. The answer will be equal to 1. In fact, any number raised to the power of 0 is equal to 1. Now let's go to the fifth law. Okay, I think we've done some few examples regarding the fourth law. Now let's take a look at the fifth law. The fifth law is just doing the division form of what we've just done. The fifth law is just the division. You know, just now we were doing the multiplication form. Now the fifth law is just looking at the division of what we've just looked at here right now. So that's the fifth law. Okay, it's the same concept. So here you'll be applying the power law and the second law mostly. Okay, now let's take a look at the explanation. For example, if I have 3 over 4, you know, this is division, right? Both of them raised to, they are not same number, but they are both raised to the same base, to the same power. Both of them raised to power 3, raised to the power of 3. This will be given as 3 over 4 times 3 over 4 times 3 over 4. You know, you can do it like this, or you times the numerator first, 3 times 3 times 3. Okay, there over 4 times 4 times 4. So this will be 3 over 4 times 3 over 4 times 3 over 4, right? Then look at it, 3 over 4 times 3 over 4 times 3 over 4. That's what it means. Okay, that this is what this means. If you say 3 over 4 to the power of 3, you mean 3 over 4 times 3 over 4 times 3 over 4. That's what it means. What you're saying is that you can multiply the numerator first. You can say 3 times 3 times 3 all over. You draw one long division line, and then you say all over 4 times 4 times 4. So it's the same thing. So in other words, if we have another scenario, let's use the alphabet to show this. Let's say if we have another case, let's say you have C over D, everything to the power of 4, then we're going to have this. This will be equal to C over D times C over D times C over D times C over D in 4 places. Okay, this will be C over D times multiplied by another C over D. Okay, multiplied by another C over D. Multiplied by another C over D. Okay, so this is the 5th law. It's about division. Another C over D. In general, let's make the general law now. Let's quote the general law. In other words, if you have in general, if you have for the 5th law, if you have A divided by B, you can see the two quotient or the two letters or numbers, they're different. They don't have the same base. If you have A divided by B raised to a certain power, let's say n, then this is simply equal to A raised to power n. You can simply say this will be A raised to power n divided by B raised to power n. Divided by B raised to power n. Okay, this will simply be A raised to power n divided by B raised to power n. It's same as this one. Okay, this is simply C raised to power 4 divided by D raised to power 4. It's same thing. So this one can be simply written. This one can simply be written as C to the power of 4 divided by D to the power of 4. Can simply be written in that manner. Is that okay? Can simply be written in this manner. C raised to the power of 4 divided by D raised to the power of 4. Likewise, this one can simply be written as 3 to the power of 4. 3 to the power of 3 divided by 4 to the power of 3 divided by 4 to the power of 3. Can simply be written like this. Okay, it's either you put in this format or you put in this format. Same thing. Is that okay? So this is the 4th law and the 5th law. This is the 5th law. Okay, this is the 5th law. Now let's take a look at an application for the 5th law. Let's take a look at an application for the 5th law. I think we choose something different to characteristically bring something unique. Okay, now let's say we have P question 1. Let's apply. We say P over R raised to the power of 7. Both of them raised to the power of 7. So P over R raised to the power of 7. Okay, this is simply just saying individually P to the power of 7 over R to the power of 7. Okay, there's nothing more to do. You just say P to the power of 7 over R to the power of 7. You raise individually, you break it down individually. Okay, then your job is done for this case. But there are more exclusive cases whose applications are very vital. Let's take a look at one of such case. Let's say if we have 4g squared, if we have 4g squared h 4g squared h divided by k to the power of 4. K to the power of 4. Then every t to the power of 3. Every t to the power of 3. Now you'll give you something like this. It's super easy. Same thing that we'll be talking about. So what you do is to evaluate this. Now look at it. Let's evaluate this one. Let's evaluate this. This is 4 to the power of 3. So you're going to say 4 to the power of 3. Okay? Which means 4 times 4 times 4. That's 64. 4 to the power of 3. There times multiplied by g squared. G to the power of 2. G to the power of 2 times this power. Because this power is talking to each and every letter and everything inside the bracket. So this power 2 will be multiplied by 3. So you say g to the power of 2 times 3. That's what you have for the power of g now. In order to evaluate the power that g has, then you say multiply by h. H only has one h, which is h raised to power 1. 1 times 3 is 3, so you write only 3 here. Okay, for the numerator. Now we evaluate for the denominator. We simplify that of the denominator. So you see, for denominator, you only have k to the power of 4 times 3. So we have k to the power of 4 multiplied by 3. K to the power of 4 multiplied by 3. Remember, the power is talking to each of these individual ones. The power is talking to this one, also talking to the power here. So what we have eventually after that is to write out what we have, right? Write out what we have. So this becomes 4 to the power of 3. 4 to the power of 3 becomes 64, right? 4 to the power of 3 becomes 64. So let's begin to evaluate. G to the power of 2 times 3 becomes g to the power of 6. So we write g to the power of 6. G to the power of 6. And then we have h to the power of 3, right? We have h to the power of 3. We write h to the power of 3. And then for the denominator, we have only k to the power of 12. We now say all over k to the power of 12. Why? Why is it k to the power of 12? Why is it k to the power of 12? Because 4 times 3 is 12. So here becomes k to the power of 12. So that's it. We've simplified this, or we have evaluated this. Is that okay? So that's that for this kind of case. Now we move on to the next one, which is called the negative indices. Okay, but before we go to negative indices, there's what we call the zero indices. Before we move to the negative indices, we have what we call the zero indices. Now for zero indices, what it simply means, I think we need to write that. We have what we call the zero indices. We have the zero indices. Zero index. So let's just use the word zero index. Zero index. Okay, for zero index, what do we have? Here, the zero index indicates that a number is raised to the power of 0, right? For example, if we say a to the power of 0, this is simply a zero index, which gives 1, right? This is a zero index. So when something is raised to the power of 0, it's simply called the zero index. When any number or letter is raised to the power of 0, is simply called zero index. A number raised to the power of 0 is always equal to 1. A number that is raised to the power of 0, any number, big or small, or any letter, big or small, raised to the power of 0 is always equal to 1. This can be explained by actually applying the laws of indices. Actually, we can use the laws of indices to explain this. For example, let's use the law of indices to explain this zero index. How we can arrive at zero index, for example. If I have a to the power of m divided by second law, divide by a to the power of n. Remember second law. Divide by a to the power of n. Then let's see how this can help us. You know, this is simply given as what? It's simply given as a to the power of m minus n, right? In our second law of indices. This is what we learned, right? In our second law of indices, this is what we learned, right? M minus n, right? Imagine they are raised to the same number. Imagine they are raised to the same number. For instance, imagine that now these two are raised to the same number. Like we have, for example, we have a to the power of m divide by a to the power of n. Divide by a to the power of n. What do we have? M to the power of m. See? A to the power of m divided by a to the power of m. So in this case, it will be like this. It will be like this. A to the power of m minus m. It will be a to the power of m minus m. And you know m minus m is equal to 0, right? Same number, you minus them, you get 0. So this will give us a to the power of 0. In any application where you get power 0 is called 0 index. Any application where you get power 0 is equal to 0 index. Okay? Any application where you get power 0 is equal to 0 index. So which means ordinarily a to the power of m over another a to the power of m will simply give you what? Simply give you 1. We simply give you 1 because a to the power of m divided by a to the power of m has been obtained to be a to the power of 0, which is equal to 1. Has been obtained to become a to the power of 0, which is equal to 1. So a raised to the power m divided by a raised to the power n equal to 1 because it's a 0 index. Because it's going to be a 0 index because this one will be equal to a to the power of 0. This one will be equal to a to the power of 0. And any a to the power of 0 is given scientifically or mathematically is given as 1. Mathematically is equal to 1. Any a to the power of 0 is equal to 1. Is that okay? Okay, now let's go to negative indices. Let's look at negative indices. For negative indices, before we go to negative indices, let's take a look at something that maybe you might understand. If I say 5 to the power of 7 divide by 5 to the power of 7. This is what we are saying. If you have same base and same power, then your answer will be 1 because this will be a 0 index. Applying it, this becomes 5 to the power of 7 minus 7. 7 minus 7 is equal to 0, right? So this becomes 5 to the power of 0. 7 minus 7 is 0. This becomes 5 to the power of 0. And in indices, we say any number to the power of 0 is equal to 1. So this is called 0 index. This is what we mean by 0 index. You will get 1. And for every 0 index, you're going to get 1. Your answer will be 1. Is that okay? Now let's move on. Now we go to negative indices. Let's go to negative indices. Negative we go to negative indices. Negative indices. Okay. For us to get negative indices, then we simply, let's say if you have if you have 1 all over 7 to the power of 3, if you have this 1 over 7 to the power of 3, 1 in indices, it means 7 to the power of what? 0. 1 in indices means 7 to the power of 0. 1 in indices means 7. Not really 7 per se. It means any of the base, the other base, whatever. If here is 5, here will be 5 to the power of 0. If here is if 9 was used here will be 9 to the power of 0. So this one simply means 7 to the power of 0, because remember we say any number to the power of 0 is 1. Any number to the power of 0 is 1. So when you see them write 1 in indices, it's simply the base that they're referring to the power of 0. So this simply means 7 to the power of 0 divided by 7 to the power of 3. Now, what makes it negative indices is that let's use the second law. So when you do the second law, you say 7 to the power of 0 divide by 7 to the power of 3. Let's apply the second law. You will get a negative index. You get a negative index. This will be, since they have the same base, we take the base to be 7, and then we say, since it's division, second law applies. So we say 0 minus 3. 0 minus 3, that's this power minus this power. 0 minus 3. Then eventually we get what? We get 7 to the power of negative 3. 7 to the power of negative 3. We get 7 to the power of negative 3. Okay. Here I'm going to tell you something again, that in indices, when you get negative indices, when you get negative index, when you get a negative index, then there's something that relates to a negative index. There's something that permanently relates to negative index. Now that thing is like this. For example, you have 7 to the power of negative. Negative means 1 all over. In indices, when you have this negative means what? 1 over. Negative means, in indices, negative means 1 over. Then you now say 7 to the power of 3. 1 over 7 to the power of 3. Okay, let's break it down furthermore. Okay, let's show it more excruciatingly. So if we have, let's say I have x to the power of minus 1. Let's start from there. If I have x to the power of minus 1 in indices, this will be 1 over. This negative, this power negative means 1 over x to power 1. You know, power 1 is same thing as just saying x. So instead of saying power 1, you can just leave it as 1 over x, right? So if that's for this. Now if we say x to the power of negative 2, x to the power of negative 2, what will it become? How will you write this for negative indices? These are called negative indices because they have negative in their power. They have negative numbers in their power. That's why they are called negative indices. That's why they are called negative indices. They have negative in their power, negative numbers in their power. So when you have this, how will you write it in fractional form? In expressing this in fractional form, this, I told you, the negative means 1 over. That minus is responsible for this, right? 1 over. And then whatever this x, whatever is here, and this power, you write at the denominator. Whatever is here, you write at the denominator. You say x to the power of 2. Okay? Vice versa. If they give you something like this, they want you to express it as negative indices, you just say this 1 all over x to the power of 2 means x to the power of minus 2. Okay? Vice versa. So if we have x to the power of negative 5, x to the power of negative 5, similarly, it means the same thing. X to the power of negative 5 means, first of all, this minus means 1 over. Means 1 over. Then you write x to power 5. Then you write x to raised to power 5. Is that okay? Then you write x raised to power 5. Okay, so that's that for that. Now, sometimes let's look at some excruciating example. if you have a to the power of 2, you say a to the power of 2 divided by a to the power of 4, a to the power of 2 divided by a to the power of 4. Okay, applying the second law of indices or doing it manually, doing this manually, this implies a times a, right? A to the power of 2 means a multiplied by a, right? Then at the denominator you have a to the power of 4, which means a times a, right? Times a times a times a. This is what you have. So if this is what you have, now let's see if we cancel out. This a on top can cancel out this a at the bottom, and this a at here we cancel out this one. So what we have at the numerator, it's 1. It's remaining 1, not 0. Okay, it's remaining 1. So you have at the numerator, the only thing that is left is 1, and at the denominator, the only thing that is left is 1. 1 is left here. 1 times a, which is a square, which is a square. So what we have at the denominator, we have this. Okay, in other words, which can also be expressed as what? If you have 1 over a square, it becomes a to the power of negative 2. A to the, this, remember, 1 all over is raised to power minus. It means raised to power minus. 1 all over anything in indices, 1 all over anything in indices means a to the raised to power minus. Okay, whatever power is here, then you put here. If this power was 5, you say a raised to power minus 5. If this power is 6, you say a raised to power minus 6. Is that okay? So that's one way of doing it. Now, if you do it this way, like not manually, like following the first law, you have a to the power of 2. You have a to the power of 2 over a to the power of 4 over a to the power of 4. Look at it. Now, applying the second law of indices, you have a, you do like this, a to the power of 2, a to the power of 2, then divide by a to the power of 4, and this will give us what? Since the bases are same, you take it as only 1a, and then you subtract the power. 2 minus 4, which is equals to negative 2. So we have a to the power of negative 2, a to the power of negative 2, which is what we got previously. Okay, a to the power of negative 2. Or you can put it in fractional form, fractional indices form, which becomes this 1 all over a square, 1 all over a to the power of 2, 1 all over a, 1 all over a to the power of 2. Okay, we can put it in this format. Okay, so that's that for that. That's that for that. So in general, let's write the general rule for the negative indices. Let's write the general rule for the negative indices. Okay, let's write the general rule for the negative indices. So the general rule for negative indices is that if you have a to the power of negative n, if you have a to the power of negative n, then this can be expressed or simplified in fractional form to mean 1 over a to raised to power n. 1 over a raised to the power of n. In general, this is what we have as the negative law of indices. The negative law of indices. Is that okay? This is what we have as negative law of indices. Now let's take a look at some excruciating example that involves so many others. Applying many laws together. Applying so many laws together, and let's see how we can solve some basic and reflective problem. Okay, because the last part will be fractional indices, which we might take in part 3 of this course, the fractional indices. Okay, now let's solve some problems. Question number 1, we solve some questions. Question 1, we say D, if they give you, they say simplify. Okay, use the laws of indices to simplify each of these. Write the answers using the positive indices. Write the answer using the positive indices. If I have d to the power of negative 6, now they say simplify this. What will you do? This is simply this is simply equal to, remember I said that this power negative means 1 all over. It means 1 all over. So you write 1 all over d to the power of 6. 1 all over d to the power of 6. Is that okay? 1 all over d to the power of 6. That's it. Because they just want you to simplify this way. What if for question 2, let's say we have something like this. We have 3c to the power of negative 4. You have 3c to the power of negative 4. If you have something to simplify this, what will you do? This is simply equal to, you say 3 multiplied by 1 multiplied by 1 over, remember c to the power of negative 4 would be what? 1 all over c raised to power 4. C to the power of negative 4 is 1 all over c to the power of 4. Right? 1 all over c to the power of 4. So once you do this, you now multiply the numerator. 3 times 1 is 3. So the next thing we get is that we get in the numerator, the next thing we get is that the numerator we get what? 3 times 1, we get 3, and the denominator we get what? C to the power of 4. C to the power of 4. So our final answer in a positive way is 3 over c to the power of 4 for this question. Is that okay? Now let's take a look at the next one. Number 3. Okay, let's take number 3. Okay, number 3. Let's take this one as number 3. S to the power of 3 multiplied by s to the power of negative 5. Now, if you look at this very well, you can see first law here, s to the power of negative 5. And you can see negative indices here, negative law here. So this, because they have the same base, ss, and they multiply this first law, but the power of this one is negative indices. So you can see two things are combined here. So what we need to do is simply, there are two ways to do it. Is that we put this one in fractional form straight away, so that we have x to the power of 3. There are two ways to do this. Either you say s to the power of 3 times, this s to the power of 5 means 1 all over s to the power of 5 at the bottom. 1 all over s to the power of 5 at the denominator at the bottom. So you now see s to the power of 3 times 1 will be equal to s to the power of 3. S to the power of 3 times 1 will be equal to s to the power of 3, okay, in the numerator. And then the denominator, you just have s to the power of 5. So which means if we reduce, we will have manually cancelled out. We will manually say this is same as saying s times s. If you want to do it this way, this is saying s times x times s all over x times x in 5 places, right? S times s times s, okay, times x times s times s, okay, times s. So if you take a look at this, you see this can cancel this. Let's take another color. I think this becomes blurry. Let's take blue. This one can cancel this. Okay, this one can cancel. This is a long way anyway. We should have done it just with first law. This can cancel this. So on top we have 1 times 1, which is 1. And at the bottom we have s squared. At the bottom we have s squared. Because only 2s remaining. So we have s to the power of 2. So this becomes our final answer for this one. Okay? Okay, so that's that for that. There are many ways to do it. Okay, that same question. There are many ways to do the same question. There are many ways to do that same question. Okay. Now let's take another one. Let's just move on, right? We can simply, let's use shorter method to solve them. Let's use shorter method to solve them. Number 4, let's say number 4, we have b to the power of minus 3, b to the power of negative 3, divide by b to the power of 8. So b divided by b to the power of 8. You see, the negative brought negative indices. You can simply use second law by saying b, you write minus 3 on top here, which is what we should have done just now. Minus 3, then minus 8. Why is there minus 8 here? Because of this division, second law. Why is there minus 3 here? Because of this number, negative 3. So this gives us b to the power of negative 11, right? b to the power of negative 11. And they say we should leave our answer in positive form. So your answer, b to the power of negative 11, means 1 all over b raised to power 11. 1 all over b to the power of 11. 1 all over b raised to power 11. Okay, so that's that. That's the answer for this one. Now let's take a look at this one, question 5. Let's take a look at this question 5. So if we have question 5, we have 4 outside. We have 4 outside, and then we have a bracket open. We have a bracket open for y. Here we have y to the power of 4. And then we have a bracket closed. And this bracket is closed and is raised to another power negative 3. Is raised to another power negative 3. So they say simplify this. They give us a problem like this. They say simplify this. So what do? This power is only talking to something inside the bracket. If you're not inside the bracket, this power is not talking to you. If you're not inside this bracket, this negative 3 power is not talking to you. This negative 3 power is not talking to this 4. Why? Because this 4 is not inside the bracket. If 4 was inside the bracket, then this negative 3 power will also be talking to the 4. So all you need to do is simply to say 4 times 4 multiplied by, just write the 4 the way it is. Then you write y to the power of 4 times y to the power of 4 multiplied by negative 3. Because this power will multiply. Third law. Multiply by negative 3. Multiply by negative 3. So this will give us, this will be equal to, 4y to the power of minus 4 times 3 times negative 3 is negative 12. Raised to the power of negative 12. Remember, they say we should not leave our answers in negative numbers. So and then we write 4. We write 4 times. Remember, y raised to power minus 12 is simply 1. You say times 1 all over y raised to power 12, right? Y to the power of negative 12 is simply 1 all over y to the power of 12. So 4 times 1 is 4. 4 times 1 becomes 4 in the numerator, and then the denominator is y to the power of 12. You just write y to the power of 12. Y to the power of 12. Okay, now let's take a look at another one that is exactly like this, but a little bit different. You see this, you spot the difference now. Let's say, for example, if we have now we put this 4 inside. The same thing, but we're going to put the 4 inside. So we're going to open bracket from the beginning. We write 4y to the power of 4. 4y to the power of 4. And then you square it to minus 3. Raised to power minus 3. Now, the difference between this and this is that this 4 was outside the bracket, but in this case, this 4 was inside the bracket. So now the difference is that this power is now talking to this 4. So first and foremost, you say 4 to the power of, let's take another color. You say 4 to the power pink. You say 4 to the power of -3. 4 times 4 raised to the power of -3 times y raised to the power of 4, y raised to the power of 4 times -3 as well. Because this power outside is talking to both of the numbers inside now. This power -3 is talking to both the y to the power of 4 and 4. 4 to the power of -3 times y to the power of 4 times -3. So I will say this 4 to the power of this means what? This one will be, for 4 to the power of this, you can simply say 1 all over 4 to the power of 3. You can simply say 1 all over 4. You can simply, because it's raised to power -3, right? You can simply say 1 over 4 to the power of 3. And then we already simplified this one before. We say this is same as y to the power of -12, right? Y to the power of -12. And this one can also be written as, so you say 1 all over 4 to the power of 3, 1 all over 4 to the power of 3, 1 all over 4 to the power of 3, okay? And then times 1 all over y to the power of -12 will be 1 all over y to the power of 12. Will be 1 all over y to the power of 12. So what we have in the numerator is 1 times 1. So 1 times 1 is 1. And then at the denominator, 4 to the power of 3, you have 64. So you can write this 64 here. So you say 64 y to the power of 12. So you have 1 all over 64 y to the power of 12. So you can see just a slight difference, because you put the 4 inside, you are having 1 all over 64 y to the power of 12. But here, because you put the 4 outside, you are having 4 over y to the power of 12 only. So you can see small changes, how it brings a whole lot of difference in the work. How it brings a whole lot of difference in the work. I think we just have to do one more, and then we stop for today. Then the next one, we will do what we call the fractional indices and exponential indices. The fractional and exponential indices is what we're going to take in our part 3 of this course. Exponential equations and so on and so forth. That's what we're going to take in our next equation. Is that in our next class? Exponential equation. And we're going to also digress to standard form. We take standard form in a separate class. We take in a separate class. Okay. So here and now, let's just solve one problem. Right? Yeah. Let's just solve one problem, and then we can call it a day for today. Let's just solve problem 7. Let's choose any of the problem and solve. Okay, we have 4 to the power of 4a to the power of -3, 4a to the power of, simplify. The question is simplify this. 4a to the power of -3, b to the power of 2, then we have b to the power of 2, all over inside the bracket 2ab squared to the power 3. So I open a bracket, 2ab squared to power 3. So this is what we have now. So we solve the numerator and then we do the denominator, right? Let's solve the numerator and then we do the denominator. This is simply saying that this 2, since it's inside the bracket, the 2 is inside the bracket, so it's going to be 2 to the power of 3. So here, the numerator is just for a to the power of 3, a to the power of -3, okay, and b to the power of 2. Just write it like that first, b to the power of 2. There for the denominator, you have here, you're going to have 2 to the power of 3. We're going to like evaluate 2 to the power of 3, which is 8. It's not 6, okay? 2 to the power of 3 means 2 times 2 times 2, okay? That gives 8. And then times, why? Because it's inside the bracket. Whatever is inside this bracket, this power is talking to it. So 2 is inside the bracket, so it's going to be 2 to the power of 3. Then times a to the power of 3 as well. So here you have a to the power of 3 as well. You have a to the power of 3. And then you have b times b. You have b to the power of 2 times 3. B to the power of 2. Then you multiply by the power outside. B to the power of 2 times 3. Times 3. The power outside. So this will lead us to, let's still write what we have here. A to the power of 4a to the power of minus 3, 4a to the power of negative 3, b to the power of 2 times b to the power of 2, there over, now 2 to the power of 3, this 2 to the power of 3 gives us 8. This 2 to the power of 3 gives us what? 8. Gives us 8. And then we have a to the power of 3. Let's write it first. A to the power of 3. Let's write it first like that. Okay. And then we have here, we have b to the power of 6. 2 times 3 is 6. We have b to the power of 6. Okay. Then the next step is to simplify now. After you evaluate, now is to begin to simplify. Now, what kind of simplification do we need here? You can see 4 divided by 4. Some people will write 2 here. You're doing good if you do that. So let's take another color to itemize this properly. We take this one. No, we use it. This we've used this. Which one? Yellow. We've not used. Let's try. The yellow is not conspicuous. 4 divided by 4, you get 1. 8 divided by 4, you get 2. So there's 2 at the bottom. There's 2 here. Okay. Yellow is not so conspicuous. Let's take something very identifying. Okay, let's take red. We say 4 divided by 4, you get 1. And 8 divided by 4, you get 2. So there's 2 at the bottom, okay? Please don't forget that. There's 2 here. Then, this one, you use second law. See, you can use second law to solve A and A, like division. Okay, you can use second law to do this. And you can use second law to also do for B. Okay, let's use second law and see what we get. Let's do second law and see what we get. So you have 1 here times 1 times, now see what I'm going to do. I'll do A to the power of minus 3, right? That's the first A. Then because this is division, this is second law, I will also say minus 3 again, right? Minus 3 again. Why I put this second minus is because we are applying the second law of indices. We are applying the second law of indices. So a to the power of negative 3, then minus 3 because they are dividing each other. Second law of indices. Then I'll say times. I do the same to b. I'll apply second law of indices. I'll say b to the power of 2. The first one is power 2. Then I will not say minus because this is division. In division, second law of indices, division becomes minus. So in power, when you're dealing with the power. So b to the power of 6. This is 6, not 3. This is 6. 2 times 3. 2 times 3 is 6. This is 6. So minus 2 minus 6. Yes, minus 6. The power. So 1, and then every 2 over 2. Remember there's 2 at the bottom. Remember? There's 2 at the bottom. Every 2 over 2. Over 2. Okay, that's what we got just now. Now the next step is our final step, probably, or second to final step, is just to simply say 1 times anything is 1, so just simply deal with this. So you have a to the power of minus 3, you get negative what? Negative 6. So I have a to the power of negative 6. Then times, what do we get for b? B to the power of what? 2 minus 6, you get negative 4, right? B raised to the power of negative 4. Okay, remember they say in our answer they don't want to see negative number in the answers. So what do you do? Let's do the final step now. What do you do is to simply put them in the fractional form. Put them in fractional form. Put them in a fractional form. Well, this one means what? 1 all over a to the power of 6. Right? 1 all over a to the power of 6. And this one means what? This one means what?
1 over b to the power of -4. No, 4.
1 over b to the power of 4. So the final stage will be 1 times 1 is 1. So numerator I have 1. The denominator I have what? A to the power of 6, a to the power of 6, and b to the power of 4. And b to the power of 4. That will be our final stage. Remember, this is for b to the power of 4. This will be our final stage. Okay? So thank you for joining us today. And the last part, we're going to take, for the last part of indices, we're going to take exponential and fractional indices and indices equation. That's what we're going to do for the last part. Okay? Thank you.